So this will be the start of the next section of notes, 6.4, and this will be going over normal distributions. So this first slide, again, we talked about histograms and how they're rectangular boxes arranged on a horizontal axis. And then we had our x-axis marked evenly spaced increments of possible outcomes, right? Again, we always talked about that. Before about how it should be equally spaced. And then the height of each block shows how much frequency there is of each one. And this will kind of relate to what we're going to be talking about now. So the next thing we'll talk about is symmetry of data. So one of the most useful properties that helps us analyze a distribution is symmetry. And when we talk about symmetric distribution, we work from a central point, and that central point goes to the left and right, and that central point is going to be our mean. And when we talk about non-symmetric distributions, that means that they're going to be either kind of swayed more to the left or more to the right, and it won't be kind of an even shape. Or we can call it a bell shape. And we'll see an example of that in a sec. So if we look at these different symmetric distributions, the first one here is called a uniform distribution, meaning that all frequencies or everything's the same. We all have the same amount of levels of each one. But if we look at a binomial distribution, it's all the data is kind of set in the middle, and then it's spread out to the left and the right pretty evenly. And then the right one is bimodal distribution, meaning that it kind of has, it's known as kind of two peaks. So it kind of peaks up, goes down, and then peaks again, and then goes back down. Again, this one's going to be more bell-shaped, and we'll talk about that on the next slide. Or in a few slides. So when we talk about distributions that are not symmetric, we kind of have to describe how the data is falling. So when gets a little confusing, but we'll talk about it on the next page. But when the tail is extending to the left, we call this skewed to the left. And again, doesn't sound confusing, but when we look at the picture, you'll kind of see why we can kind of mix it up. And when the tail extends to the right, we call that skewed to the right. And we'll see some diagrams on the next slide. So these ones are going to be non-symmetric distributions. And so on the right here, again, if we look at this picture, it looks like the data is leaning to the right, so that's skewed right. It's the opposite. We always want to talk about the tail end of it, meaning that it's skewing to the left. This one, the tail is going to the right, so that's skewed right. And then this is another one called a bimodal distribution. Again, multiple peaks, and they're not symmetric. Again, if we go back to the other one, this is pretty symmetric, right? If I cut a line down the middle here and fold it over, it would line up perfectly. This one, I could not do that. So that's why it would not be symmetric. Another thing that we really won't get into too much detail, but continuous variables and distributions. Again, we really won't talk about this too much, but if we did have a histogram with a continuous variable, then we would have a smooth curve. But we really won't get into that too much. So one thing about systematic distributions and skewed is how does that relate back to the mean, median, and mode? So when we have something that is symmetric, the mode, the mean, and the median are all going to be the same. We saw that in our last unit when we talked about different problems where the mean was way off because those are called outliers. So if we took the salaries of everybody at Starbucks, right, including the CFO and all that. Well, the CFO makes a lot more money than every barista, and there's a lot more baristas working at Starbucks than the CEO. So that's why it would be totally off, and the mean, median, mode would be totally different. That's why if we take out some of the outliers, the mean, median, mode would be more around the same range, because again, then it would be more like this would be more skewed when we have a really large data set. So when it's skewed to the left, again, talking about the tail end of it, we can see that the mode would have a higher value because, again, if we look at the peak of our bell-shaped curve, we can see that the mode, what happens the most. And then the median would kind of fall a little bit less than that. And then the mean will kind of be the smaller value. And then that switches when our data is skewed to the right. Again, now our mean would be the highest value and our mode would be the lowest value. So those change constantly, but those are all going to be our central tendencies that we've talked about that kind of help us identify our data. So again, normal distributions are everywhere in real life and you may not even think of it. So I kind of found some examples to kind of talk about newborn weights. Again, the frequency of how many newborns, again, maybe they did a study at one hospital and you can see that on average, right, a newborn baby would be about 7.5 pounds. And again, this is symmetric. The data kind of is all towards the middle and then it levels out on each left and right. Another example would be SAT scores, right? There's not going to be that many people scoring a really low score and there's not going to be that many people scoring a perfect score. But again, the data is evenly distributed. And then the last one that I found as well is NFL retirement age. Again, the frequency is on the y-axis and then the age is on the x-axis. And again, we can see around 33 would be the average, but again, it is evenly distributed. So a lot of things that we see in real life have this shape if we collect all that data. So some of the properties of normal curves. So a normal curve is symmetric, and we call it bell-shaped because it looks like a bell. So then any random variable whose graph has this characteristic, we would call that normal distribution. And then so when we talk about that, again, our horizontal axis would be the number of standard deviations away from the mean. And we'll kind of talk about this on the next slide. And then we'll also later in the week talk about z-scores. But when we talk about a graph that looks like that, we call that standard normal curve. Again, I'm not going to be quizzing us on that, this stuff, or the vocab, but just know that, again, when we have our data all evenly spread out, we would call that a normal distribution. So to kind of sum everything up with what we kind of talked about, when something is symmetric, our median and our mean are going to be the same value, right? They should be exactly equal along with our mode. And then again, when we talk about bell shape, that means it's going to be tapering off rapidly to the left and the right to basically zero. It'll be even out, and we'll see kind of some diagrams of that on the next page. And so when I was talking about that is when we talk about a normal distribution, the space under here is really talking about the area or the percentage of how many people fall into that category. So again, if we were talking about SAT scores, right? If someone had an SAT score of A, say maybe 1,000, I want to know how many percentage of people have SAT score from A amount, say 1,000, to B amount, say 1,300. Well, then this area or percentage of our bell-shaped being covered up, that would represent how many people, or the percentage of how many people would score between those two values. And so the area underneath this curve is going to always be 1. So maybe this area would be maybe 0.75. That means 75% of people would fall between those two data points in a normal curve. And again, just kind of going over some of the vocab, a normal curve instead of like normal distribution. And we'll be kind of talking about, and we can also see here that smack dab in the middle is going to be our mean. So some properties of normal distributions is the spread is completely determined by the standard deviation, which we have found in our last unit. right? We've been able to calculate that, and that's basically, again, the average of how far each data point is away from the mean. So when we identify that, the area under any of these sections is completely determined relative to the mean. So we'll find the mean, find the standard deviation, and that'll help us kind of set up our bell curve or normal distribution. So one of the things that we'll do is we'll accurately find these percentages, but there's kind of a rule of thumb or a imperial rule. So about 68% of data lies between one standard deviation. So that means kind of adding the standard deviation, adding it, and then subtracting it once, and that area would represent 68%. And we'll see a visual on the next slide. If we do 2 standard deviations, that's about 95% of the data. And this is, again, a rule of thumb that we can kind of use to estimate. And then the last one would be 3 standard deviations away would be almost majority of the data. 99.7% of those people or the data would fall in between, at least between positive and negative 3 standard deviations. And I think that'll make a little bit more sense when we look at a visual here. So when we look at a visual here for the mean, what I'm talking about is when we subtract one of our, so if I take the mean and subtract 1 standard deviation, sometimes we label this as negative standard deviation. And then between here would be taking mu, or the mean. I guess I can kind of write that too. Mean is mu. Minus, or adding 1 standard deviation, and we can also label it as just 1 standard deviation. So that means that this area right here would represent 68%, would fall between 1 standard deviation. Then we can also then say if we take 2 standard deviations. So that would be taking mu and subtracting 2 standard deviations. So that would be another way of saying it is negative 2 standard deviations. Same thing on this side, I would take mu and add 2 standard deviations, which would be 2. Well, this data, again, I don't know how this is going to look, but if I highlight all of this in red, that would represent 95% of our data. And there'll be a nice picture on the next page, but I'm kind of just showing you how we're getting these values. And then lastly, again, if we take mu and subtract 3 standard deviations, or negative 3 standard deviations, and add 3 standard deviations, maybe I'll try this in blue. All of this data, and highlighted in blue, would then represent 99.7% of people. Again, if we kind of go back to these data curves here, right? If I wanted to find, obviously these don't have standard deviations on there, but again, if I highlighted around this much area here, that would represent about 68% of people. Then if I highlighted this section here, that would be about 95%. And then if I basically highlight almost the entire thing, except maybe the little ends there, that would represent 99.7% of our data. So if we kind of look at this picture here, this kind of summarizes it pretty nicely. Trying to think of anything else to kind of mention here. And we'll be looking at some graphs for your homework, like that'll be already marked out, saying like this is 65, this is 68, this is 71, this would be 62. I'm just coming up with random numbers, 59. Those would be 56, 74. And I might give you all these data points, and you're going to have to look at like, oh, what's the mean? Well, what's smack dab in the middle? Our mean is 65. And then I'm going to ask, oh, what's your standard deviation? Well, I have to look at what is it changing by? So from 65 to 68, I'm adding 3, adding 3, adding 3. Going backwards, I'm subtracting 3, subtracting 3, and so forth. So our standard deviation would be 3. So just by looking at these normal distributions, we are able to kind of identify those values, and you'll be doing that in your homework. But let's look at this first example. So suppose that we have 280 students taking an exam and the normal distribution of the scores are treated as normal. So again, they're telling us that it's a normal distribution. That's why we can kind of use these tools to be able to find that. And we want to find the number of scores falling between 2 standard deviations. Well, if we know that it's 2 standard deviations, that's going to represent 95% of our data or people. So if 280 total people found that took this class, we would we would multiply 95% or 0.95 by 280, and that would get us about 266 students that fell between 2 standard deviations away from the mean. So again, using and this is kind of a rough estimate. And again, we'll calculate more specifically later in the week. One more example that we'll kind of talk about is kind of finding the percentage. So the distribution of heights of an adult American men is approximately normal. So again, they're stating that vocab word that we kind of briefly talked about, with a mean of 69 inches and a standard deviation of 3 inches. So we want to find what percent of men have height above 72 inches. And again, keyword above. And about what percentage of men have heights between 63% and 75%. So on the next page, I kind of have some more space here. And the first thing I'm going to do is draw an actual graph, a distribution graph. So we can just kind of draw a curve here. And we know that in the middle here is going to be our mean, which is going to be 69. 1 standard deviation away would be adding 3, so that would be 72. Another standard deviation would be 75. And then lastly, adding 1 more standard deviation would be 78. Now we're going to go the opposite way. I'm going to subtract 3, so we get 66. Subtract 3, get 63. Subtract 3, get 60. And again, I'm going to kind of mark this as our mu. So it says, what percent of men have height above 72? So that's going to be this area right here. So what we need to do is figure out how much percentage of height there is between 66 and 72. So we know in this area right here, 66 between this area right here represents 68% of our data. So that means that if we take 100% and subtract 68%, we would end up with, what would that be? 32%. That means that the area in blue and this area would have to add up to be 32%. I'm gonna draw arrows here. Well, again, I only want to find what is the percentage of people who are above 72 or higher. And again, this is symmetric, so it's going to be an equal amount. So again, if I take half of 32, we can say roughly 16% of men have a height above 72 inches. So again, using kind of this imperial rule to kind of estimate how many people or the percentage of men have a certain height above 72. The next example says, what percentage of men have heights between 63 and 75 inches? So if we go back to our picture here, between 63 and 75, we can see that that is 1, 2, and 1, 2. So 2 standard deviations on both sides, it's equal. So we know that if it's 2 standard deviations away, and again, we talked about that here, 95% are within 2 standard deviations, meaning to the right and to the left. So we didn't have to really do much work on this one. This would just be 95%. So 95% of men have a height between 63 and 75 inches. I think that's gonna be the last slide. So please try the homework. It's again one of those online, so it gives you kind of feedback if you got it right or wrong. Again, the homework really wasn't too much of new stuff. I threw on some other practice stuff, including the 5-number summary, and then being able to use your calculator to find the mean, standard deviation, and the mode. So give those problems a try. I'll be back tomorrow and answer any questions and pass back the exit slip that we took on